Hello everyone. Thank you very much for being here today. My name is Lam. I am a doctoral student from the Center for Machine Vision and Signal Analysis, and this is my pleasure to present our work, StressNAS, Affect State and Stress Detection using Neuron Architecture Search. This is a collaboration effort between CMVS, PIX, and Ubicom Research Center at University of Oulu, Finland. Stress is an undeniable part in our daily life. Human brain can easily get stressed. For example, if we check and see an email from human resource, we get stressed. Or if we walk on the street and somehow accidentally see our ex-girlfriend or boyfriend, we can get stressed. Or when making this representation video, although we know that this is recording, we still get stressed. Moreover, long-term stress can have a negative effect on our physical and mental health, and this is not good. With the current evolving of smartwatch, we ask ourselves, can we develop accurate stress detection system from physiological signal? State-of-the-art method on stress detection usually using conventional machine learning methods such as linear discrimination analysis, random forest, decision tree, and adapose to achieve good classification results. In the advent of deep learning, recent approach proposed using deep neural network for stress detection. However, despite the efforts, this remains a challenging problem. This is because human physiological signals are complex, and the task of design deep neural network is tedious. It requires a lot of trial error and expert knowledge. Therefore, the question is, can we use neuron architecture search for stress detection problem? Let's talk a little bit about neuron architecture search. The idea of neuron architecture search is to use deep neural networks to automate the network design task. The core idea is utilizing reinforcement learning to build an RNN or an LSTM controller to generate architectures. From these candidate architectures, we can train and evaluate them to find normal and reduction cells. We then create the network by stacking these cells together. Although this is a compelling idea, one of its drawbacks is that it is very expensive. For example, to find an optimal architecture for classification problem on ImageNet, this framework took more than 7 days on 500 GPU. And it is clear that this type of resource is not available for everyone. Recent developments on auto machine learning areas introduce new methods to perform neuron architecture search without any training. The idea is to score an architect at initial time to predict its performance. Assume that we assign binary indicators for every activation unit in an architecture's F. We then can represent a linear region xi by a binary code ci. That I is the data point. The best performance architectures have the least correlation between their binary codes. This is because it is difficult to disentangle two inputs with the same binary codes, which means it is less expressive and usually lead to lower performance networks. For example, here, we can clearly see that best performance architectures tend to have very low correlation, while low performance architects have higher correlation. Using this idea, we can significantly reduce the time to search for optimized model. In this work, we utilize the WISAT dataset to build our stress detection system. The WISAT dataset is a high-quality multimodal dataset for human affective detection. The data were collected from 15 persons using the chest wound and the wristband. We only use the data from the wristband that include the blood pressure volume at 64 Hz, the EDA at 4 Hz, skin temperatures at 4 Hz, and the label at 700 Hz. It also contains the acceleration data. However, we think that these motion signals are not reliable for stress detection as they can introduce more bias into the trained model. We then populate our modality using the higher frame rate of the label. We sample our data by applying the sliding window of 60 seconds and the stride of 0.5 seconds. We then calculate the min, max, mean, and standard deviation of the sample data. In total, we get around 132,600 data samples. We also filter the EDA accelerator and acquire more features from the raw EDA, skin temperatures, accelerator, and BBB signal. More detail are provided in our paper. Finally, we transform the 1D signal to 2D representations by transforming the time series data to filter bands. These figures present our framework. Our framework takes the EDA, BBB, skin temperature filter bank, and mixed data as input. For each type of input, we generate 10,000 architecture candidates to search for the optimal cell. We then perform ranking and training only 10 best candidate networks. We also build some handcrafted deep neuron architectures, including a multi-layer perceptron, a fully convolutional network, and a residual line deep neural network model for comparisons. We report the result for 3 states: neutral, stress, and amusement in Table 1. Our StressNAS model outperforms both conventional machine learning methods and handcrafted deep neural network for most of the modality combinations. Table 2 shows the binary classification of stress and non-stress. Interestingly, manual design neuron architect perform similarly or worse than traditional machine learning model. In contrast, StressNAS model provides a significant improvement in almost all settings. Table 3 presents the best detection accuracy for each study subject for 3-stage classification test. In general, the detection results are evenly distributed among other subjects, with a small bias on subject 3, 10, 13, and 16. In conclusion, firstly, our paper proposes a fast atomic method for generating deep neural networks that achieve good accuracy for stress detections. Compared to other methods that take multiple days on hundreds of GPU, we only require 2 days on 1 GPU. Secondly, although this is not clearly stated in the paper, our framework produces lightweight models that are suitable for resource-limited devices such as smartwatch or mobile phone. Finally, thank you very much for your attention. Feel free to contact me if you have any questions. Cheers!